Okay, with this lecture, we're going to kind of wrap up our discussion on soil colloids. But with this, I'd like to give you a little bit more depth and information into soil colloids, and especially silicate clays and their organizations and shapes and how they are established. So remember, we talked about 1-to-1 and 2-to-1 silicate clays. And the 1-to-1 clays contain one tetrahedral sheet and one octahedral sheet, whereas the 2-to-1 clays contain an octahedral sheet that is sandwiched by two tetrahedral sheets. And remember that the most common 1-to-1 type of silicate clay is a kaolinite, whereas the 2-to-1s include smectites, vermiculites, and illites. Now here's just kind of a schematic of these 2-to-1 and 1-to-1 clays. On the far left here is a typical kaolinite where we've got one tetrahedral sheet and one octahedral sheet. And then the sequence starts again, tetrahedral, octahedral. Whereas a 2-to-1 clay, we have an octahedral sheet that is sandwiched by a tetrahedral sheet on the top and one on the bottom. Now we designate our 2-to-1 clays a few different ways. And one of the ways that we can do this is by their shrinking and swelling capacity. So the main driver that tells us about the shrink and swell capacity of these 2-to-1 clays is what we call, it's actually called a C spacing. It's basically the spacing between the individual clay particles. And you'll notice on the smectite, the spacing is rather large compared to like a vermiculite, or in this case a fine-grained mica where it's very narrow. Okay, and the last designation of clays is it's called a chlorite. It's actually a 2-to-1 so we've got two tetrahedral sheets, one octahedral sheet, and then we've got this hydroxide sheet here too. And we're not going to spend a lot of time talking about those because they're fairly rare. You're not going to see them around here. But they do exist, so maybe keep that in mind, that they're a 2-to-1 organization in addition to our 1-to-1 and 2-to-1. Now, this spacing means that with these 2-to-1 clay minerals, there's a lot of room in here for water molecules and other cations to enter, and that space allows those clay particles to expand. And smectites are the highest expanders, vermiculites somewhat intermediate, and then these fine-grained micas, they tend to be not non-expanding, or they swell just a very little bit. And it's interesting that these 2-to-1 clays that are smectites, micas, they're arranged in such a fashion that potassium is actually trapped in between these inner layers. And that's an important thing. These types of soils occur around here with regularity. As you head east out of Moses Lake, a lot of the clay particles are these 2-to-1 micas with potassium trapped in the inner layers. And so the soils, believe it or not, have quite a bit of potassium in them. So these 2-to-1 clays right here that are the fine-grained micas, they tend to predominate in our area in central Washington. Okay, the highly weathered oxisols and ultisols in high rainfall areas in the tropics, they tend to be dominated by these kaolinites. But they also, as you've seen with our soil horizonation stuff, tend to have a lot of oxides of iron and aluminum as well. The smectites and vermiculites and fine-grained micas are most predominant in alphasols, mollisols, and vertisols. Okay, remember the vertisols are the shrink and swell types, and so you'd expect these to be more of a smectite type of clay. Mollisols, it depends on where they're at, but these tend to be less weathered compared to the 1-to-1 clays. Here's a table that shows you some of the characteristics of these different colloid types. The colloid types are listed over here. We have organic matter just kind of as a reference. and then smectites, vermiculites, chlorites, kaolinite, and so forth. And what we're looking at here is their charge and its dependency on the pH. Okay, so look at organic matter. This is cation exchange capacity. These units are a little bit different from what you're used to seeing. We usually talk about cation exchange capacity in terms of milliequivalents per 100 grams. Well, this is the scientific notation, and it's the same thing. So organic matter has a cation exchange capacity of 200 centimoles per kilogram. It also has a CEC of 200 milliequivalents per 100 grams. The number is the same. And so you can see how these clay particles differ from each other. Okay, organic matter is the highest, vermiculite's quite high, smectites are somewhere in between, and then the fine-grained micas, we're starting to get down into lower cation exchange capacities. Okay, and I told you that these things are pH dependent, and so remember, as the pH goes down, we have the potential for soils to have an anion exchange capacity. Okay, and you'll notice that these guys right down here, the kaolinite, gibbsite, girthite, and allophane, these are what you're going to find in highly weathered soils. Okay, so our soils, it's very unlikely that you'd see a soil with an anion exchange capacity. But there is some potential, because we're dealing usually with these fine-grained micas, and so there is some potential that as the pH goes down, our cation exchange capacity can also go down. Okay, so the different cations in the soil is largely dependent on the climate, the climatic conditions, and so iron, aluminum, hydroxide, and hydrogen, these are the most predominant cations in humid regions. And what we mean by humid regions, areas of high rainfall. Whereas calcium, magnesium, and sodium dominate in low rainfall areas. Okay, and since that's where we're at, those are the ones that we're going to focus on. These are the four cations that I want you to pay particular attention to: sodium, magnesium, potassium, and calcium. These are what we call the basic cations, and they dominate in our western soils here. So some things to make note of here: sodium and potassium, you'll notice these line up on top of each other. They both have a +1 charge as ions, whereas magnesium and calcium, they line up on each other. They have a +2 charge. Okay, that's important because I told you before that soils have to maintain a charge balance. So in other words, let's say that you've got a magnesium that is on the cation exchange complex. If you want to kick that magnesium off, you've got to replace it with 2 sodiums or 2 potassiums, because those 2 cations only have a +1 charge. You can exchange a magnesium straight up for a calcium because they're both +2. Okay, but if you're trying to exchange a magnesium for a sodium, you've got to have 2 of them to maintain that charge balance. And this brings us to something that is fairly common in soil science. We call it base saturation. And so basically it's telling us what percentage of the cation exchange capacity is occupied by these 4 basic cations, which are calcium, magnesium, potassium, and sodium. Okay, don't get confused here and include aluminum or iron or hydrogen or anything else. The only basic cations are these 4 right here. So someday on a test question, I'm going to give you calcium, magnesium, potassium, sodium, iron, aluminum, and hydrogen, and you're going to know that you need to exclude the iron, the aluminum, and the hydrogen from this base saturation calculation. Okay, and so again, this tells us the relative amounts of these basic cations in relationship to the ability of the soil to exchange those cations, and this is the equation. Okay, now recall that base saturation, the units for cation exchange capacity are milliequivalents per 100 grams. And so, not coincidentally, when you have a soil tested, the calcium, the magnesium, and the sodium are expressed in these same units. It makes the math easy. But potassium is a little bit of a problem because it's usually reported in milligrams per kilogram rather than milliequivalents per 100 grams. But to make it easy, all you need to do is take the value that you get for potassium and divide it by 391, and the resulting value is then milliequivalents per 100 grams. And if you don't believe me, I've shown you the math down here at the bottom. You can pay attention to that or not, but if you want to convert potassium from milligrams per kilogram, this is parts per million, by the way, it's the same thing, you need to divide it by 391 to get milliequivalents per 100 grams. And so if your calcium, magnesium, and sodium are now expressed in milliequivalents per 100 grams, and your CEC is also expressed in milliequivalents per 100 grams, you have the ability to calculate base saturation. So here's kind of a practice problem, and what I want you to do here, and this is going to be an assignment that I want you to turn into me, is I want you to create a calculator with Excel where you can take calcium, magnesium, sodium, potassium, and cation exchange capacity, and from that I want you to calculate percent base saturation. But in addition to that, I want you to calculate individually what percent of the CEC is calcium, magnesium, and sodium, and potassium. Okay, I think you have the ability to do that, knowing what you know already about Excel. So I want this turned in by, let's see, looking at my calendar here, I want this to be due by February 8th, which is Wednesday. Great. So one of the other things that is important about our clay mineralogy is its ability to hold on to things. And we're going to talk about organic compounds for just a minute, but it's other things too. It's not just organic compounds. Soil colloids can control the movement of pesticides and other organic compounds in the groundwater to the groundwater. And this is kind of an important thing, because if we apply chemicals to the soil, their fate is of interest. And the reason it is that if these chemicals get into the water, then they tend to hang around. But if they get bound to soil particles, then the soil microbes will tend to eat them up and kind of degrade them and break them down, which is a good thing. We don't want chemicals hanging around forever. And let me show you kind of a graph of maybe the difference, two extreme differences. Okay, what you're looking at here is the amount of a toxin absorbed by the soil over time. And look at, this is a montmorillonite right here. Montmorillonite is a 2-to-1 clay. It's a shrink and swell clay. And look at the amount of toxin that soil is able to hold compared to a kaolinite. Okay, remember, a kaolinite is a 1-to-1 clay. It has a low CEC, and the ability of that kaolinite to hold this certain toxin compared to montmorillonite is quite a bit less. And so if you think of this in practical terms, if you apply a chemical to a kaolinite, that soil is not going to hold that chemical nearly as well as a montmorillonite. And so if that's the case and you're expecting this thing to break down, the potential for this to leach into groundwater in a kaolinite soil is far greater than this montmorillonite soil, where it tends to hang on to the soil surfaces. So that's the practical application of understanding the CEC in the soil and what it affects, or how it affects the transport of chemicals in the soil.